Hello everyone, I'm Norman Wildberger. Today I want to share with you the exciting news that the Algebraic Calculus 1 course is going to go online in a public fashion on May 1st of this year, 2020. That means that it will be freely available, at least the first part of it will be freely available to the general public all around the world. And it's entirely online. Everything is online, the videos, the notes, the work problems, the homework questions, and additional material all available to you. So it's very exciting, and I want to tell you a little bit about the course. For those of you who don't know about it, it's a very different kind of approach to calculus. So we're taking this classical, beautiful subject, very powerful subject, but we're thinking about it in a new way because we want to make the foundations of the subject much stronger. So the subject has always been really important practically, has formed a bedrock for engineering and science, physics. But there's always been these logical difficulties, even from the early days of Newton and Leibniz, espoused by Bishop Berkeley, tackled to a certain extent by Euler and Lagrange and so on. But the directions that some of those great mathematicians laid out have not always been followed by the modern textbooks. The modern textbooks have a kind of a uniformity of view. They're very applied oriented ultimately. And I think there's a missing stratum of actual logical coherence and setting up the foundations of the subject coherently in a way that really does not require any philosophical underpinnings. That's what we're going to do with the Algebraic Calculus 1, okay? And it's the first of several Algebraic Calculus courses that I plan to present. In fact, I'm already working on Algebraic Calculus 2, which will also be coming out this year in a beta form. Now, this course here has actually been running for 2 years online to a select group of people. About a couple of hundred people have been going through the course, adding all kinds of really positive and important suggestions and contributions, and some of those are now incorporated and will be further incorporated into the course. So it's a work in progress, but it's very exciting. And I want to tell you about it, and then I want to encourage those of you for whom it's appropriate, and that won't be everybody, okay, but it'll be appropriate for those people who are really aspiring to really have a high-level understanding of mathematics. I want to tell you about how to join. Okay, so there's 10 chapters. Okay, the chapters roughly, correspond to maybe a week's work in an intensive undergraduate course, but we're going to lay them out one every month. Okay, so this will be like the May ones, June, July, and so on. So the first topic is the affine plane, where we set up the geometrical foundations for the subject, which turns out to be affine geometry, not Euclidean geometry. Okay, so areas of rectangles, base times height, that formula doesn't actually even appear. Okay, it's a kind of a red herring. The real best way of introducing the whole notion of areas for the integral calculus is via determinantal formulas coming from linear algebra ultimately. Okay, so that's a big shift. We're making a lot of connections with linear algebra in this course. Then we move to signed areas, starting with triangles and then working way more generally to oriented splines, so that we're in position of describing the signed area of an oriented spline. And it's not what the usual calculus textbooks do. They usually think of having a function and the area underneath the function. That's not the best way of thinking, as it turns out. Okay, then we move to very important algebraic underpinnings of the subject that go back to a remarkable German mathematician called Johann Faulhaber, who actually set up an algebraic direction for both differential calculus and integral calculus. Basically, he defined the derivative and the integral before Newton and before Leibniz. He did so in the context of trying to establish formulas for sums of powers. This is a very important development that's usually not expressed in standard calculus courses. So there's lots of interesting formulas and some new insights in here. Then we move to the main objects of interest, which are actually curves in the plane and the associated ideas of motion from physics and engineering. So curves actually are more general and fundamental objects than functions. If you take a classical course in calculus, you'll learn all about functions. And functions are great, okay? But when you go to curves, you're really going up a big step, okay? You really start to understand things a lot better. And a lot of the sort of fussy aspect of things that you need to do with functions disappears if you do it correctly with curves. And in some sense, this is really just going back to understandings of the 17th and 18th century mathematicians. For thousands of years, curves were the main thing, and functions were relatively modern innovations. Then we move to tangents. So we get a little bit of the differential calculus here, even though most of the course is focused on the integral calculus, which is ultimately easier than the differential calculus. But tangents, we can define tangents for curves, and we do so without the usual limiting of secants kind of story, because we want to avoid any kind of reliance on having to perform an infinite number of operations. Okay? We want to stick entirely within an algebraic framework, maybe a very simple-minded algebraic framework, just high school algebra with addition, subtraction, multiplication, and division. Okay? It turns out that we can do that, surprisingly. Okay? Limits are not necessary, real numbers are not necessary. A lot of the infinite processes encoded in transcendental functions can be avoided if we think about things in the right way. That's what we're aiming for with this course, to really understand what the right way of thinking about things is. Okay. So then we have some applications to topology in physics. So our understanding of signed areas allows us to shed light on some interesting questions about curves in the plane. And we connect with very important application of calculus, perhaps historically the killer application, which was the understanding of Kepler's laws via Newton's laws of motion. Now, we're not in a position to entirely describe that story. That'll be algebraic calculus 2, or maybe even algebraic calculus 3 by the time we've completely understood that. But at least we're going to start making contact with that very important problem. Then we make what might appear a kind of a shift. We talk about the discrete calculus, which connects quite closely with the sums of power story. So whether we're talking about curves or whether we're talking about sequences, there's parallels, okay? So the differentiation and integration for curves, that has a parallel with sequences when we talk about differences and summation operators, okay? And there's a nice story there, and I want to elevate that discrete side of the subject to almost an equal level with the analog side, which is usually presented. So usually the discrete side is little mentioned, if at all, okay? But for us, it has almost equal importance. And as we'll carry on with the algebraic calculus series, you'll see more and more the importance of this discrete point of view. And then we get to really, I guess, the really quite novel aspects, where it turns out remarkably that the areas of curves can be pinned down precisely with just high school algebra if we restrict ourselves to the most fundamental kinds of curves. And they were introduced over here, and they turned out to be the de Castelnau-Bézier curves, which are also crucial for work in design and architecture and modern graphics. So these de Castelnau-Bézier curves really ought to play a central role in any calculus course. So we are putting them center stage really for the first time. Okay, these are absolutely the fundamental things. And remarkably, we're able to actually have a complete theory of integration for these things. So this is like a key point that distinguishes this course from any other on the planet. And then we come to the fundamental theorem, which is, yes, the highlight of the course. But it's not the fundamental theorem that you may have heard about, which is usually talked about in calculus courses. It's a variant of it, which also talks about the relation between differentiation and integration, but it's a very different looking kind of formula and gives you new insights into what's really going on. So even professional mathematicians are going to learn a lot from this chapter on the fundamental theorem, but they will probably have had to ingest some of this prior material first. Okay, so there's lots of interesting stuff happening, but I want to emphasize this is not all of the calculus, okay? This is just a first course in calculus, suitable for maybe like a one semester course at a very high level class of students, okay? But we're going to lay it out in a relaxed kind of fashion, one of these chapters per month, so it'll take us most of a year to get to the end. And these first 6 topics are completely free to the public, so you'll be able to get a good sense of the algebraic calculus, its power, its beauty, its utility, and the fascinating challenges that arise by being able to look at things, fundamental things, really important classical things, in a new way, in an exciting new way. So I want to clarify now, who the intended audience for this course is and for this series of courses. So the courses are at a high level, at some level, because we're really aiming to nail down the logical structure of this course. We don't want to leave anything under a carpet. Okay, we want to lay it all out, and we want to, at the same time, substantiate all the results with computational analogs, with examples, explicit examples, with real computation. So we're never just doing abstraction. We're doing abstraction, and then we're seeing how that abstraction works in a computationally explicit form. So I have this approach to mathematics, okay, which is very different from many of my colleagues, that it all has to be on a page. It all has to be visible, and not just some of it, but all of it, okay? It has to be checkable. There has to be a paper trail for everything. So even elementary things, in fact, especially elementary things, really have to be nailed down in such a way that we can all go and look at it and be critical about things, okay? So I'm trying to get people to spend a lot more time and effort on the foundations of the subject. Okay, we're not relegating that to set theory or logicians or philosophers. It's really our responsibility as pure mathematicians to set up the subject coherently so that the applied mathematicians who are using this mathematics can do so as effectively as possible. It's our responsibility. And so I want to encourage that. And I want to, help you to move in that direction too. But you have to have quite a high level of motivation and talent, okay? So who is it aimed for? It's aimed for undergraduate math majors who are interested at least in pure mathematics, okay? So that's in some sense the primary group, and it can be first-year students up to second, third, fourth-year students. So a wide range of students are going to find this potentially very interesting and informative. In fact, I would like colleges to start thinking about, the way we teach calculus now, is that set in stone? Is it possible for us to think about, doing things in a different way? How about taking our best students and making a separate class and teaching them in this more advanced, more logical way? So they get a broader appreciation of real pure mathematics, not just learning a whole bunch of techniques to solve engineering problems, which is great and important, okay? But I think especially math majors need to see the logical structure much more clearly. They should be confident about the mathematical logic behind the theories that they're learning. So that's really the primary intended audience in some respect. However, engineers and physical science students, okay, with mathematical maturity, who have an interest in mathematics, they are also going to find this very interesting, because even though the course is mostly theoretical, it has a lot of computational aspects. So physicists, engineers, other scientists are going to learn practical ways of thinking and working things out. Mathematics graduate students, so even students who have already done an undergraduate degree, they're working on a PhD or master's, you can benefit a great deal by studying this subject very carefully, okay? It's going to open your eyes to a new way of thinking about mathematics, a new way of thinking about what the logical coherence of mathematics really is, that we have to be tighter. We can't just say stuff. The stuff that we say has to be supported by actual concrete definitions that are not, in question, that are not relying on some assumptions off the page or off the universe. Okay, so graduate students, you are potentially going to learn a lot. And also, High school students, if you're a final year high school student and you're really talented and you love mathematics, and you're yearning to learn more, actually this course will be very good for you. Okay, you might not be able to understand everything at the first go, but most of what I say is laid out, I think, pretty explicitly and hopefully clearly. And you will be able to follow a lot of it. And if you work on the worked problems and the homework questions especially, put a lot of effort in there, you'll be able to go really far in this direction. Okay, because actually the underpinnings are relatively elementary. What you will probably need as we go on in the course is more contact with some linear algebra. You may not have done linear algebra before, and that turns out to be an important ingredient as we move along. And so I will suggest to you, if you're going this direction, is have a look at my Wildland Alg course. Okay, it's my online videos, and work your way through a dozen or two of those. Okay, that'll give you a good grounding for the linear algebra required to make this happen. And the general public, not just young people, older people, retired people, people who have, however, a strong mathematical skill base and, very crucially, are motivated. They want to learn. They want to learn some new things. Maybe they want to even get to the stage where they can make some discoveries on their own. Okay? So this course is very unique in that I am going to be bringing you up to the forefront of knowledge in certain areas. Okay? So there will be opportunities for you to make really original discoveries. Okay? You will have to work hard to do that, but it is possible. Okay? So this is, I think, a great opportunity for the general public with a mathematical interest, and I know there's lots of people out there that fit that bill, to roll up your sleeves. Okay, roll up your sleeves and join us and do some work and learn a lot of interesting new things. It's very, very exciting. And finally, my fellow mathematicians, I know you're reluctant to put aside all those years of work that you've put into the regular calculus. You would rather think that that's the right way of thinking and you're not going to really entertain possibilities otherwise. But I can assure you that if you do take the bold step, of saying, okay, let's see what happens if we look at things in an entirely new way. Okay? If you are willing to take that step, you will benefit so much from this. Okay? I promise you this. You will learn a lot of really interesting and important things that will be able to affect your research and also your teaching. Okay? So it will give you a new view of what mathematics education might be. Okay, so how do you join up? Well, it's easy. It's an online course which is at Open Learning. So you just go to Open Learning, you sign up, you get an account, it takes 5 minutes, and then you join the course. Okay, here is the URL for the course. It's starting May 1st, and then when May 1st comes around, you'll be able to access the first chapter. And then when June 1st comes around, you'll be able to access the second chapter and so on. And you can make comments because Open Learning is a very socially engaging platform for courses. It's a great platform. It's been developed here in Australia. Okay, so I've had a lot to do with Open Learning over the years, and it's really great, and they've made a lot of progress. So it's very attractive, and you'll like the setup, I think, and it's conducive to chatting, to conversing, to submitting ideas, to interchange of ideas with other participants. So I really do encourage you to join us. And I'm talking about myself and also notably Dr. Anna Tomskova. So Anna is a very smart PhD in mathematics. She actually was a student at UNSW for a while. She's now teaching in Uzbekistan, but she's helped me enormously in setting up the course. She's done a lot of work on worked problems, on homework questions, made a lot of the diagrams and the apps that you'll see throughout the course. It's quite a visual course with lots of pictures and also some interactive things. And she's helping me in moving forward and making this even better. So I can't thank her enough for all the work that she's already done on the course. And there will be others also that will be helping as we go along. So I do hope that you're going to join us. I hope you'll be patient, at our efforts to try to lay out this subject, but I'm sure you'll find it very rewarding ultimately. And it's a brand new way of thinking about a lot of classical, beautiful mathematics, and I think there's a lot to learn. I'm Norman Wildberger. Thanks for listening.